So I want to go ahead and assign oxidation numbers to these various species. And remember, oxidation numbers, they're similar to cations and anion charges, but they're man-made. So there's some slight differences with those. So the first one is Na solid. So this is sodium solid. Remember, elements in their standard state, or elemental states, natural states, wherever the case may be, their oxidation numbers are always going to be 0. So this one is 0. So in their natural states, it's going to be 0. Same thing with chlorine gas. Remember, chlorine is diatomic, Cl2 gas. So its oxidation number is going to be 0. And again, natural states are just by themselves in nature. Let's take a look at this other one here. Let me erase this. This is calcium permanganate. So calcium is positive 2. So its oxidation number is going to be positive 2. So for these ionic compounds, the charge of the metal and the charge of the non-metal are normally going to be their oxidation number. So calcium is positive 2. Now, there's some priorities you have to assign. Basically, oxygen is always negative 2. So I'm going to say oxygen is negative 2. So that's its oxidation number. Manganese, transition metal, we're going to have to figure it out. We're not sure what's going to be. A couple ways we're going to do this. I have 1 calcium, so that's positive 2. I have 4 oxygens, so times 4, that's negative 8. This compound is neutral, it's going to be 0. And so there's 1 manganese, so times 1. And so that manganese has to be a positive 6. So I need to have a total charge of positive 6. So that manganese now, its oxidation number has to be positive 6. So again, the ones I circle are actually oxidation numbers. It's not the total charge, it's the oxidation numbers. Calcium is positive 2, there's 1 of those. Oxygen is always negative 2, that's the oxidation number. There's 4 of those, total charge of negative 8. To make this neutral, because this is a neutral compound, manganese has to be positive 6. Let's take a look at the other one here. This is methane gas. We've done so much of it in terms of fluid structures. Hydrogen can be positive 1 or negative 1. Usually it's positive 1. In this case, when it's combined with carbon, it's going to be negative 1. So hydrogen is negative 1, so that's its oxidation number. There's 4 of them, so times 4. So again, negative 1 is the oxidation number, negative 4 is the total charges of them. I got 1 carbon, and again, this is neutral. So to make it work out, that carbon has to have an oxidation number of positive 4. So carbon is positive 4. So again, pay attention. Carbon is positive 4 in this case because I have 4 hydrogens. Each one is negative 1. Let's take a look at this other one here. This is a dichromate ion. Total charge is negative 2. So I have chromium. There's 2 of them. So we're trying to figure out what that oxidation number is going to be. Oxygen, I mentioned before, always assign it negative 2. So that's his oxidation number. So the ones I circled, that's the oxidation number. There's 7 oxygens, so times 7. So it's a total charge of negative 14. The charge of this compound is negative 2. The charge of all the chromiums combined have to be positive 12. Because positive 12 plus negative 14 is equal to negative 2. So in this case, chromium has to be positive 6. Each one is positive 6. There's 2 of them. Total charge of positive 2. So again, the answer is positive 6 for chromium, negative 2 for oxygen. Let's look at the last one here. This is sulfuric acid. In this case, if hydrogen is not really bonded to either carbon or metal, it's going to be positive 1. So hydrogen is positive 1. There's 2 of them, so that's positive 2. Oxygen, I remember, is always negative 2. So oxygen is negative 2, hydrogen is positive 1. There's 4 oxygens, so times 4, negative 8. There's 1 sulfur. Again, this has to be neutral, so the total charge has to be 0. To make this neutral now, sulfur has to be positive 6 total. There's only 1 of them, And so in this case, sulfur is going to be positive 6. So again, it's kind of like when you're trying to figure out the charges of these cations, you're kind of working out backwards. A few things to remember. Oxygen is always negative 2. Hydrogen, usually positive 1. We had an exception with that. Stuff like sulfur, manganese, carbon, you have to figure it out based on either hydrogen or oxygen, etc. So let's take a look at this chemical reaction. We're actually going to do this one in the lab, and we want to see what species is oxidized, reduced, oxidizing agent, reducing agent, etc. So a couple things. I've already assigned oxidation numbers to each one of these species. So again, chlorine and iodine in their natural state, I'm going to give it to them 0. So they're diatomic, Cl2, I2, etc. For sodium iodide, sodium is positive 1, iodide is negative 1. So halogens are normally negative 1 unless they're in their natural state there. Same thing with sodium chloride. And we want to see what gets oxidized, what gets reduced. Always like to write this table on the top of my paper. If I go from left to right, so if I go from 0 to positive 1, 0, positive 2, negative 4 to negative 1. If I go in this direction, it's oxidation. It means I've lost electrons. If I do the opposite, so if I go from like positive 2 to 0, it's reduction. It means I've gained electrons, etc. This direction, oxidation. This other direction, the opposite, is reduction. So let's take a look at chlorine. So chlorine goes from 0 to negative 1, so that means that's reduced. When something's reduced, it's always the oxidizing agent. Sodium stays the same, positive 1 to positive 1, so nothing changes in that case right there. Iodine goes from negative 1 to 0, so negative 1 to 0, so that means it gets oxidized. So if it's oxidized, it's the reducing agent. So whenever you try, like say this case, it gets reduced, write down automatically it's oxidizing agent. This gets oxidized, write down it's reducing agent. And again, it's based on the fact that chlorine gets reduced, it means it oxidizes iodine. It takes an electron away from iodine. Same thing with this one. This gets oxidized, so the iodide gets oxidized, it's a reducing agent, which means it gives an electron to the chlorine. That can be a little confusing, so reduced, oxidizing agent, oxidized, reducing agent. Let's go to our last one. So this is lead 2 oxide plus carbon monoxide is equal to lead solid and then carbon dioxide gas. So again, I've already assigned oxidation numbers to that. Pay attention. For carbon monoxide, again, oxygen is always negative 2. The carbon is positive 2 because it's a 1-to-1 ratio. But for this one, oxygen is still negative 2. That's always the case. There's 2 of them, so copper is positive 4. So again, copper is going to change. Now, oxygen won't, but copper will. So a few things. For lead, I go from positive 2 to 0. So I go from positive 2 to 0, so I'm going in this direction. That means it gets reduced, so just to make sure. So that's reduced. That's the oxidizing agent. The oxygens don't change, negative 2, leave that alone. Copper now, or carbon, I'm sorry, goes from positive 2 to positive 4. So positive to positive 4. It's why I always like this table. This way it always makes sense. It goes in this direction, so it gets oxidized. It's going to be the reducing agent.